Okay, folks, it's time to start. First, are there any questions about the either the videos or the online material? If not, I will go through the next set of videos, which are on the discovery of the Higgs boson. All right, no questions. If you have any questions, just send a chat or pipe up. So I'm going to share my screen. All right, folks, this is last call. Otherwise, oh, there's a chat message. Let me see what that is. Which homework? Homework 2? So somebody had a question about the homework? Well, why don't you put some more detail about your question, and I'll answer it after I finish this I'll leave enough time at the end to answer it. All right, so the next set of videos after the broad review of use cases is one particular use case, which was included in that group, which is the discovery of the Higgs boson. And so I will summarize. So in this lecture here, I will summarize the videos for that field. All right. So this is the identical slide we've shown already, and it sets the scene for the discovery of the Higgs boson. We have a giant accelerator, 17 miles in circumference. That's shown on the top part of the slide, and it has the accelerator, and then here it has the injector, which gets the protons up to speed before inserting them in the ring. This is a proton-proton collider. The largest one in the US at Fermilab is a proton-antiproton collider. At this energy, it doesn't make that much difference whether you collide protons or antiprotons. In general, better to collide antiprotons because they're more likely to smash up when hitting protons, but for large enough energy, that doesn't make so much difference. And we will see later even more detailed pictures of events, and they will always have a straight line, which is where the protons are coming to hit each other. And then the interesting events will have sprays of activity to the side. And one actually does not take, one only takes a small fraction of the events, and you effectively trigger the events by looking for ones that are potentially interesting because they have things going on. This accelerator is not studying the typical event. And as we've shown before, here's this giant experiment, and it has 3,000 people and lots of institutions and countries. So this is sometimes called big science. And we will have the bottom here, it describes the amount of data and the computing model, and we'll have a better picture of the computing model later on. And the data is run through a multi-stage workflow where the raw data is reconstructed, and the reconstructed data is summarized, and the summarized data has physics done on it. And as we'll see, the data analysis is at some level quite simple, although the actually analyzing these events like you see in the middle, and where the analysis means effectively taking, well, here you have all these lines, these are the particles. You effectively map those tracks which are detected in wire chambers, typically, which record particles traveling through them. They're bent in magnetic fields, so you can measure their momentum. And also there are neutral particles, which are measured by what happens when they collide with heavy metals such as lead. And here is this famous picture, the first picture of, which was in the first paper from the Atlas experiment. There are these two big experiments which are aimed at looking for the Higgs, but they are about the same size in all measures, tons, people, countries, institutions, number of computers, and they're called Atlas and CMS. Indiana University is part of Atlas. I happen to know more about CMS, but that's just because I used to work with those people. And this picture here on the top is the raw data, which has a little bump here. And this bump is the Higgs boson. This is the mass of produced photons, 2 photons. You detect the photons and then measure their momentum vector, because you know where they hit, and then you, from the catastrophe that happens when they hit lead, you measure their energy, and so you get the momentum, and from the momentum you can calculate the mass of the Higgs. And Higgs decays in various ways, and 2 photons is one of the more prominent ways. We will have a little discussion of Higgs decay later on. And this is the world's simplest analysis by the scale of deep learning and things like that. This is taking this data, which are these black dots, and fitting the data to a smooth curve. That's this thing here with the dashed line here, which is just a polynomial in this mass, and then a background, which is this bump here. So the bump has a certain form, which is well understood, and so you fit the bump plus the background, and then from these, you find from the bump here that the mass of the Higgs is just over 126 GeV, where a proton's 0.98 GeV, so it's much heavier. And there is no deep learning whatsoever here. It is basic data analysis. And this sort of, when I wrote these notes, I remember what happened when I started making my decision about what research to do. one of the professors at this was at Cambridge University, showed a plot like this, which was a bump. And he said that bump was a particle. And I was so staggered by such a concept that the bump was a particle that I decided to do research in that area. Most of the other professors described solving differential equations in those days, and I found those less astonishing than this. And you will see these error bars here. This particular type of data analysis is extremely sensitive to error bars. You need to understand error bars. And some of the Colab or Python notebooks are devoted to studying errors. And this one thing one should know about all these experiments is that their error goes like this. The error in the measurement goes like the square root of the number of events. So if you have 2,000 events, which is the number in this bump, the error goes like the square root of 200, which must be around, well, it's 45, something like that. So it's not a huge error. I mean, 2,000 is a non-trivial measurement. But they started taking data and they had to run for longer. I mean, you gather data uniformly in time. So this was some years of running. And they ran for long enough to get enough events so that that bump was statistically significant. We will show some computer-generated pictures where the bumps are not significant. All right, so this is some more detail about that picture, that the LHC is actually runs out between France and Switzerland, and it is quite low, far below the surface, 330 feet. It has lots of superconducting magnets, which are used to get low power, high magnetic field, and you need the magnets to persuade the protons to stay running in a circle, because if you don't bend the magnets, don't bend the protons, they will just shoot off at a tangent, and that's actually what happens at a collision. You stop bending the proton roars out of the accelerator, and then you get your collisions. So, and these protons are traveling pretty fast. And as we met, there are 2 big detectors and 4 pretty big detectors. And it uses, of course, quite a lot of power, even though it is using low power comparatively low power magnets. And it's reasonably expensive, billions of dollars. And it costs a lot of money to run, to actually power it. And also the collider doesn't always run. It takes little multi-year pauses when the physicists sit down and analyze the data, and the accelerator engineers improve the accelerator. Okay. So, sorry, these are the 2 large experiments I've already mentioned, ATLAS and CMS. And I don't think the names are very important. They are roughly the same design of experiment, but they make different technical choices in all sorts of areas. And the reason you have 2 is very simple. You don't really believe an answer if it only comes from one experiment. And if your experiments are this complicated, there are so many differences, you're unlikely to make the same mistake in both of them. And these experiments themselves cost $500 million. And this is largely funded by the Department of Energy. And it's funded at many, well, here it says that it's $777 million a year. That was a few years ago. it's probably gone down, not up. So now let's look at some of the computing issues. The software to the accelerator came online in 2009. The software to analyze the data was started on at least 10 years before that, and the basic decisions were made around that time. And in those days, remember the first cloud came online itself in 2008. When the decisions were made about how to analyze the data, clouds did not exist. Commercial clouds, there was no hint that they would exist. And so this particular computing model used is called a grid. And if you like, it's a sort of distributed cloud. It basically says we will take computers all over the world and join them together to address the total computing needs. And it's done, however, in a hierarchical fashion. At CERN, the accelerator, that has a so-called tier 0 computing center. And that tier 0 computing center has about a quarter of the total computers. I'm sorry, I have a cough. Then we have tier 1 centers, which are essentially one per country, or actually one per country per experiment. So Brookhaven and Fermilab correspond to the ATLAS and CMS experiments, and they are tier 1 sites in the USA. And you will find tier 1 sites scattered across the globe. Moscow, Taiwan, Spain, France, and so on. Amsterdam, Rutherford Lab in England. And actually, I did my final PhD exam in the Rutherford Lab in the research area, which would correspond to the particle physics activities at the Rutherford Lab. Because that was, at that time, Rutherford Lab had a very, by these stick scale, tiny accelerator. But most of these, in the past, instead of having these giant accelerators like those at CERN, you had multiple small accelerators, where the Fermilab accelerator is the largest in the USA, and they haven't built one since then. They tried to build one near Dallas, but SSC superconductor, super collider or something, and that was canceled. And so CERN is the only large accelerator of this type. There are lots of somewhat smaller accelerators still running. They tend to focus on accelerating different particles. The CERN accelerator accelerates protons to hit each other. The other accelerators accelerate electrons, heavy ions, and things like that. And you can see these numbers here. Here, this is probably around 2016, 800K CPU cores, 750K, so that's quite a lot. And storage is almost an exabyte of storage. And they're running 2 million jobs a day just analyzing the data from the Large Hadron Collider. And this, they're analyzing both the real data and the Monte Carlo data. In order to understand these complicated accelerators, you have to generate fake events. And actually, that's what this is the field I used to work in. That's why maybe I chose it. And one of the things I used to do was to build the Monte Carlo programs to simulate the results of what happens when you take an experimental apparatus and observe events in it. And you need that because they're so complicated, these experiments, unless you run real events, well, effectively real events through them, you will not be able to understand them very well. And so typically from either an equal number or maybe more data is taken by the Monte Carlo events than by the real events. And they enable you to interpret the results because you can see from the Monte Carlo what problems you have in the experiment, because these experiments have obvious geometric problems, and where the different parts of the apparatus join, they have problems, and there can be fake effects generated when particles hit the wrong thing. Pretty complicated. So this is a picture from 2016, and it shows, here is the website I took it from, and it shows the data running around the world, starting somewhere in the middle here is CERN, and then it's sent around the world to do its processing. And here we have, at this time, there were 365,000 jobs actually running at that time. They have almost 800,000 cores running at this time, and of which a quarter would be at CERN. So this is actually not as powerful as clouds, but remember, I say this model of computing, which actually sort of works, has similar properties to clouds, because in a cloud, you would take these 800,000 cores and situate them in the same place or one or two places, not thousands of places like you have here. But those idea of hyperscale or huge data centers did not exist in 2000. Now, they did exist when the LHC started in 2009, because that's when Amazon started. And ever since LHC has started, people have asked the question, should we have used clouds rather than grids? Because clouds are actively researched, they're developing, whereas grids are just what they are, they're sort of similar to what they were in 2000. The idea is you just take a bunch of clusters around the world and link them together, which is not terribly different from a bunch of clusters in the same place. You could argue that there's some communication costs, but the communication cost is acceptable. So the grid is actually quite effective. The management overhead of trying to manage all these disparate computer centers is, however, quite high. But there is another huge positive about grids. You can get these distributed computer centers to pay for themselves. Namely, if a university, which would be a tier 2 site, is going to be part of this grid, it probably will donate its cluster so that it can support the physicists in its physics department working on this experiment. So this thing, so we had 200,000 cores in CERN. You'd have to buy those with the EU allocation to CERN. So it's actually a cost to the central project. But probably most of the other 600,000 are not costed to the central project. They're effectively donated by the participants. So there is a fiscal model here, which is quite important. Well, here's a picture from, actually it was a talk given by Ian Bird on SlideShare. And comes from this 2016 time, which shows at that time there was, these numbers here are not quite consistent, but there's somewhere around 50 petabytes. These numbers here add up to 49.4 petabytes, the numbers here. These are the 4 large experiments at the LHC, ALICE, ATLAS, CMS, LHCb. I won't talk about ALICE and LHCb because they weren't aimed at studying the Higgs. They were aimed at studying different, ALICE was sort of a heavy nuclear type experiment, and LHCb was studying the B meson, which is a very important quark. And here is the tier 0 center, which actually it was now up to 300. Okay, cores and 250 petabytes of storage. So this is, of course, this just looks like a cloud. If you took a picture of an Amazon or Google data center or Microsoft Azure data center, they'd look like this. Okay. So effectively, CERN Tier 0 is a cloud. It's a cloud funded by European Union and devoted entirely to, well, not totally, because CERN does other things, but a lot of this Tier 0 center is devoted to the LHC. The other important feature of this experiment, at least one important feature, is the huge number of people. We mentioned that they have thousands of people on each experiment, and so when you look at the papers, most of the papers is a list of the people. Here's the Atlas collaboration from their first paper, which announced the discovery of the Higgs boson. And they even, well, there's so many people maybe who died while the thing was being put together, because just if you have 3,000 people, some will die. It is sort of quite interesting. So this is truly big science, which some people don't like because it's so big. On the other hand, if you look inside Google or Microsoft, they will have this number of people devoted to their recommender engines or to YouTube and things like that. So an individual project inside a company is certainly of this size. Here is physics. This is what I used to study. So, and actually, I used to calculate the probabilities of this. I didn't actually calculate the Higgs. The Higgs was not so important when I studied this field, because I stopped studying this area in around 1980. And what happens if you look at protons, they're made up of gluons and quarks, and the gluons can produce this so-called triangle diagram where top and bottom quarks run in a circle. Higgs couples strongly to the top and bottom quarks because it couples to the mass, and the top and bottom quark are very massive. On the other hand, the gluons don't like to make top and bottom quarks, which are massive. They prefer to make the light quarks for obvious reasons. It's less energy cost to create them. So there are these various diagrams where the protons have to have a really intense collision. And there's a picture later on which shows you the probability. So this is very rare, but although it's very rare, it's very distinctive. There are various rare events. One takes a fermion and an antifermion. It's actually, this antifermion has to be plucked out of a proton, which is not so easy because a proton has no antiquarks in it, except virtually. But with a tough enough collision, you can create virtual antiquarks. Those form one of these so-called weak interacting vector bosons, W and Z, and then the Higgs can easily be produced from that. All right. And here are similar types of diagrams which can also produce Higgs. And they all come from plucking quarks, antiquarks, or gluons out of the proton and then going for these very, very unusual collisions. All right, here's a more detailed picture of these two of these types of things, the gluon fusion, and we have these triangle graphs, which we mentioned, producing the Higgs boson, and then the Higgs boson itself has to decay. And these are called Feynman diagrams. Richard Feynman got the Nobel Prize partly for inventing these things, and given these diagrams, you can do calculations of their estimated size, and people have done that. And when they designed the experiment, they had already gone through the these types of pictures, calculated the expected decay rates from a Higgs. They did not know the mass of the Higgs. In fact, they didn't even know the Higgs existed. But they thought it existed, and they thought it was in this mass range they discovered it in. And so they were able to actually design the experiment to be sensitive to what was likely to happen. And so then that the bets that they made turned out to be correct, because the Higgs did actually look a little like it, sort of like it was meant to look. And people had pre-calculated those consequences. Here is just a diagram about the so-called standard model. The Higgs sort of confirmed the standard model. It has these 6 quarks with it's interesting to see the variation of mass in these particles. The neutrinos are less than an EeV. The one that's best understood, the electron neutrino. And the heaviest particle here is 173 GeV, which is the top quark. And then here along we have the Higgs at nearly 125 GeV. And gluons are all over the place. You never see them because they're confined, as are the quarks. You never see quarks or gluons. You see photons and electrons and muons and tau particles and their neutrinos. They can be seen because they're real particles, but quarks and gluons are not. Photons are, of course, real. And Higgs is a real particle, as are the Z and the W. So some of these are real particles and some of them are virtual. You can never take them out of separate them, because they're bound so strongly together. And the discovery of the Higgs essentially confirmed this so-called standard model. And people are desperately trying to destroy the standard model, because it would be more interesting if it was wrong. Then we'd have things to study. Oh, here's a picture I think I may have shown before. It's of one of these magnets, and it came from a photography competition. And it's just a picture of a couple of these magnets. I told you, the magnets, you have a whole string of them because you've got to keep these protons running around in a circle. So all accelerators have magnets. Here is this, I think it's an accelerator in Germany. They all look the same, so the LHC will look similar to this. All right, so now we come a little bit, we start looking at actually what you do. And this type of work I did continuously for about 20 years, studying this type of problem, because the analysis that you see for the Higgs boson is very similar to the way all physics experiments are analyzed. Because they all consist of looking at events and counting events as a function of the properties of the events. And so events are very important. So I call these counting experiments. And the simplest example of a counting experiment is what you see every day today, which is polling for the election. So that's a counting experiment. You have an event which is somebody casts a vote to the poll, and remember that if you look at these polls, they have around 1,000 people. Sometimes they have 2,000. Well, anyway, they're 500 to 2,000 people roughly in size. And there is a reason they're that size. The reason is that if they're much smaller than that, the statistical error, which is the square root of the number of counts, which here the count is the number of people who make a particular choice. So if that's not the full sample size. So if you have fewer than 500, or you might even think you need 1,000 sample size, then the square root of n becomes too big. On the other hand, you have in the polling experiments a very serious systematic bias, because you have all sorts of unknowns about the demographics and how you choose people of the right demographics. And so there's some sort of compromise. So there's some so-called systematic error. And that systematic error says there's no much point in getting, you can reduce the statistical error by taking a poll of 10,000 people, but it's probably not worth it because your systematic error is too high. In the physics experiments, we have systematic error, but it's much more controllable and understandable. It corresponds to the laws of physics, not the psychology of people. And so you can typically increase the size of physics experiments to very large numbers and still have valid results which are not biased. All right, so this is a really common data analysis type. And there are a whole set of, there's a Colab, and the first Colab, it just generates a Higgs experiment. And it's the first thing it does. If you remember that Atlas experiment, it had a background which sloped. And so the first example on the Colab is generating random events which are distributed in a sloping fashion. I'll come back to that. Maybe I won't have time in this lecture, but there is at the end of these slide decks a discussion of how to generate sloping events. And here is the number of, these are bins. So all of this work is done with histograms. And of course, if you look at Matplotlib or Excel, they all support histograms. So histograms are always used in counting experiments because you have a set of answers. Those answers measure properties, and then you classify those events by the properties. And you not only have original properties, but you have derived properties. So in the case of the Higgs, the original properties are the properties of the produced events, such as the number of, how many particles are produced, what for each particle, you know, its type and its momentum. And so, but then you did calculate derived properties, which in the case, which are say, all right, let's ask the question, if these two photons form a Higgs, what would be the mass of the Higgs? And then you'd use relativistic kinematics to calculate the mass of the Higgs. So you're always histogramming basic quantities or derived quantities. And so this histogram came from that thing. It ran through a sample of events which were carefully selected to be interesting, and then it calculated the mass of the Higgs. And this is the smooth, relatively smooth curve. It is not smooth because there are only 42,000 events in this plot. And so, and then there are going to be 15, no, sorry, here we have, yeah, we have 15 bins. And so the number of events is maybe 2,000 or something in each bin. And we have the square root of 2,000 as a typical error for each of these bins. And so when you're looking for a Higgs, which will pop up in the middle here of the plot, you have to be a little careful that the Higgs is significant. The bump from the Higgs can be seen compared to the fluctuations in this so-called smooth background. And here to show you why the poor experimentalists had to keep on running. Instead, if you had a factor of 100 less data, it would sure not look smooth enough to see a Higgs boson. So this is the same plot, but just running with 1% of the data sample. Now here we come, and that same Colab generates both the background and the Higgs, first of them independently, and then they join them together. And if you look at the Higgs, the Higgs has a property, which is the width of the Higgs. And if you look at the Higgs particle has a quantum mechanical width, which comes from the fact it's an unstable particle. If you look at stable particles like protons, they do not have a width because they're a real particle and it is observable. A particle like the Higgs, which decays, So that decay, due to quantum mechanical uncertainty, smears out its mass and gives it a width. But that width is quite small, less than 10 MeV. And so it's tiny compared to the size of these bins here. Here we have 2 GeV bins. So the width of the Higgs as observed is nothing to do with its quantum mechanical width. It's entirely due to its measurement uncertainty, because you're calculating everything. You saw those events, they look messy, and that messiness and just the quantum mechanical fluctuations implies that there are errors in what you calculate. And so you need to, so the poor old experimentalists have to work really hard to reduce their measurement error. And people say, well, it's, let's make all this data freely available so anybody can do it. But when I used to do these experiments, the first year after the experiment is done, is devoted entirely to understanding errors, reducing errors, calibrating, because there was probably in the case of Higgs, tens of thousands of detectors. Each of those has to be calibrated because they're always tending to drift, and maybe some of them are even wrong, so you have to remove them. And that is the amount of initial data engineering is horrendous in these experiments. And there's no way that people outside the accelerator experiments could possibly analyze them. Anyway, so in this particular Colab, it looks at the 2 possible measurement widths for the Higgs, 2 GeV or half a GeV. Now, if you have a particle if you have an entity which is got statistically generated measurement errors, those measurement errors will always be Gaussianly distributed. You always get Gaussian distributions when in the limit of everything being large. And for these events, everything is large. Even if you only have a few events, the properties which make the measurements are the properties of the particles interacting with the produced particles interacting with the particles in the detector. And actually, that's a much bigger number. And so these errors are nearly always Gaussian. And so anyway, in this particular Colab, we use a Gaussian distribution for the Higgs particle. And so it looks, but it's still going to look pretty messy because there are only 2,000 events. And here is the Higgs added to the background. Here's the Higgs here, and here's the result, which is not so clear. Here we have we plotted some error bars. You can see the error bars are not very convincing. This is the estimated error, the square root of n. And you can see this one here, these two are just about pop out a little. And if we reduce the number of events, it's completely hopeless. The signal is no bigger than the error bar. And if we do if we measure the Higgs more accurately, half a GeV, which I think is more like the experiment, then the signal is much better. They pop out much more clearly. And here, this is what you might call your data artistry. When you're doing histograms, you can choose the bins, the size of the histogram. You can choose everything about the histogram, the beginning point, the bin size, and the end point. So you can see for this particular Higgs with this number of events and this measurement error, 1 GeV or half a GeV bins are much better than 2 GeV bins because the signal of the Higgs becomes clearer. Here's the half a GeV bin. Even so, notice by going to half a GeV bin, I've reduced the number of events here to a little over 500, and we have just fluctuations here which confuse the analysis. All right, so now we come to a little more sections, starting to look at this in more detail. And I taught my first course in statistics in a long time ago, 1980s, and this was the types of thing. I used to study this type of event in that course, this type of analysis, because it was the dominant. And I was in the physics department at Caltech, and I say this type of analysis dominates essentially all physics experiments. And so here's some topics which one could go through. There are, in these slides, there are some remarks about some of them. So this just says that LHC physics is dominated by these few principles: the square root of n, the central limit theorem, the properties of random variables. And even the physicists, remember, these are physicists studying quantum mechanics. In quantum mechanics, everything is probabilistic. When two protons hit each other, there's nothing deterministic. When two balls hit each other, the result is deterministic. Depending on their initial angle and velocities, the result is completely determined. That's absolutely not true for quantum physics. And when two particles interact, the answer is any number of things can happen. It just has different probabilities. So there's a mixture between the physics probabilities and the statistical probabilities. However, in all cases, the events are independent. I mean, the event number one and event number two are not correlated. There's no memory. The proton doesn't remember what the previous proton did. And so when you take these different measurements, you can treat them as independent. And when you treat them as independent, that's when you can apply these powerful methods. Now, I introduced the so-called data, information, knowledge, wisdom pipeline, where wisdom is that the Higgs exists, and you can use this pipeline and to understand what this type of analysis is doing. So the raw data is what you record in the accelerator. It's the measurement in the detector devices, the energy deposited in the lead, the signal when the particle goes through ionized gases, which is how you measure the position of charged particles, the bending in the magnet, which you just do by actually, it's a pattern recognition problem. You have to take the signals in the chambers which measure positions of charged particles and join them together to produce individual particles. So what's raw data and what's data? But this raw data to information goes through several steps, because the data is the collisions happen. You select some of that data, you clean it up and write it to tape. Then you run the information offline. There's a trigger done online, so that reduces the signal because you can't afford to record all the events. Then you convert it into this specification, which is a set of particles in the event, which have particle type, momentum, and things like that. And now those are the random variables, which you study. And that's where you use your physics intuition to do things like calculate the photon masses, which you expect to be able to see a Higgs on. And then the knowledge step is calculating all these histograms and these fits and things like that. And I say wisdom comes from taking that result and persuading the world that the Higgs exists. And people have persuaded the world the Higgs exists. So you have 25 megabytes. So this is some statistics of showing how big this stuff is. Every event is 25 megabytes. That's because you have this huge apparatus, and that every detector in that apparatus is recording its stuff. And it's, I guess, reduced to 1.6 megabytes if you suppress the zeros. You have, this was an early stage, it will be more now, 40 million possible collisions per second. And you end up with a petabyte of raw data per second. And that has done, then you use some simple information to try to record for later analysis events that could possibly be interesting. And then you go from these 40 million to 100,000 events per second. And you then apply yet further triggers, and you end up with storing 100 megabytes of data per second. So well, here's just some more pictures of which are similar to ones we've had before, but they have a little more information. This thing here, the protons and antiprotons are perpendicular to the slide. So they're not two protons are perpendicular to the slide. And a typical, notice these things here are GeVs. This is the energy going sideways. If you look at a typical event, the normal event that happens when protons collide, the amount going sideways is a fraction of a GeV, because that measures the size of a proton. The proton in suitable units is around a GeV in size, and that's when they just sort of do a little small collision, which is the typical collision, everything is limited to that GeV number. Only when these quarks and gluons inside them do a drastic collision will you reach these giant amounts of sideways energy. So you can't measure the energy in the direction of the proton, because that's already huge. These protons are really going fast with lots of momentum. So the energy in the direction of the protons is irrelevant. Well, the thing you can look at is the energy perpendicular to the protons. And that's what triggers the event. And this is meant to be some Higgs event, and it actually has, as energy is conserved in the event, you measure everything, you can find some missing energy, which has a direction and a size, and that shows that, well, it's not so bad. Of all of this, you're missing 28 GeV. There's presumably some, well, it could be neutrinos, which you can't measure, or else you just missed a charged particle. This is yet another picture, and here are these are these stars. These are the photons producing signals as they go through. Probably, well, it used to be always done with lead. When I did these experiments with photons, we always used lead to record the photons. And now they actually do them better nowadays. When I did them, we had rather crude measurements which were not done in a vertical, not done so you could read out the photon directly. But now they arrange the measurement things in tars so you can just read out the direction of the photon. So these are photons which have no charge and so don't produce a signal in the chambers. They produce a signal in the lead. And these yellow or orange things, orange it says here, are the charged particles, which are bending because they're in the magnetic field. There's a magnetic field to keeping the protons in place in the accelerator, and there's a magnetic field in the apparatus so that you bend the produced particles and measure their momentum. And you need the momentum to be able to recalculate the, when you calculate, if you produce charged particles, you want to calculate the mass of the thing that was produced, you need the momentum of those particles. So here's quite a nice plot which shows you numbers and how many, let's see how many, All right, so we have 17 orders of magnitude here. This just shows you, this is the total cross section up here. It's measured in barns. And I told you the cross section, which is the total probability that the proton does something, is similar to the size of the proton. Because you can, at the crudest classical level, you can think of the proton as a ball running through space. And typically those balls miss each other and they nothing happens. And the size of the region in space, which measures how big they are, it measures their cross section, which is quite small, 10 to the minus 24 centimeters squared. Not a very big number. And the linear size of a proton is roughly the square root of this. Is measured in Fermis or femtometers, and that's 10 to the minus 13 of centimeters. And up here we have events of various types. Here's producing a bottom quark. Here's the total cross section. Here's producing jets, which are particles going off with large transverse momentum perpendicular to the protons. As a function, and this declines as the transverse energy increases. And then we have all these special particles, Higgs decays, and either to photons or to being produced by gluons and things like that. And here is the actual event rate corresponds to 10 to the 16th events per year. What's written on tape, sorry, what's the first level trigger? The big trigger is 10 to the 12 events per year. What's actually accepted is another factor of 1,000 down, 10 to the 9th per year. And then over here, we have how many, what the Higgs does for some of these decays is more like 100 per year. So we go from 10 to the 16th per year to 100 per year. And so we're really looking for a pretty small needle in a pretty big haystack. Haystack is 10 to the 16th, and needle is 100. Now, as they improve the LHC, everything gets bigger. This number here, 10 to the 16th, gets bigger. And this number here, the ratio remains the same. And so you produce more Higgs per year. As you increase the event rate, you obviously have to improve the trigger, because you don't want to keep on writing more and more data to disk. And well, here's this is just yet another picture of here's a Higgs decaying to 2 muons, and these green things here are the muons. One thing that it says up here is worth noticing. The detectors have memory. And as you increase the event rate, every time you look at the detector, it doesn't just have the event you're interested in. It has all sorts of other events. In this case here, at the time this experiment was done, every real event actually had around 30 events written in it. Now, the 30 events were not so confusing, because they consist of 2 protons hitting each other and just grazing off each other and producing fast particles going down the beamline, but nothing's transverse, because I told you, a typical event doesn't give you more than a GeV transverse, and we're looking up here at 200 GeV, or large numbers. We're looking at these really so-called hard collisions, when those quarks really, the tiny probability of finding a top quark inside a proton is realized, and those top quarks collide with the anti-top also in the proton. So all of that happens at some tiny rate, and quantum mechanics calculates these probabilities. That's what the quantum mechanical collisions, those Feynman diagrams, tell you. Well, this is, we usually study Atlas. This is a picture of CMS, which is, I say, very similar. Here we have so this is lead. So here we have a lead crystal. I think W is that Wolfram. I don't know what W is. Anyway, they have 76,000 lead crystals, which, when photons go through them, scintillate, and you measure that scintillation energy. And so this is full of interesting detectors. And all these detectors using pretty nifty physics. There's a nifty physics of electromagnetism to produce these to produce a superconducting solenoid to bend the particles. And so everything is surrounded by iron solenoids, lead scintillators, and gaseous charged particle detectors. And there's a whole, I mean, if you do experimental physics PhD, you would learn how to build some of these apparatus. And this one is the photon case. These green things are the photons detected in the lead scintillators. This is 2012. You can see how these shoot out perpendicular. It's very striking. Whereas most of these action is going forward and backward. And this is the CMS early measurement of a Higgs in this mass region here from 120 to 130. And this we saw for the Atlas experiment. This is the CMS equivalent with a signal over background. This looks as though it has somewhat more data than the, that's about the same amount of data as the Atlas case. And of course, this thing here is called the background, and this little blob here is the signal. And you need to take enough data so that you can distinguish the signal from the background. And these, these errors here correspond to the errors in the measurements. So these are the actual measurements. This thing here is this red thing here is the smooth curve run through the measurements, which are just fitted with classical fitting to a chi. Typically, it's probably a chi-squared fit was done to produce these curves. Well, I've already. So this is actually something you don't do when you're polling. When polling, you're not looking for small signals. You want to find which signal is biggest. Here, we're looking for small signals. And we need to find a region where the background is small enough, because if I have a signal n sub s and a background n sub b, the error goes like the square root of the sum. And we need to make that error small compared to the number of events in the signal. So if the background is too big, the square root of the background will overwhelm the signal. And as I mentioned, the thing that's true in polling, systematic errors, is true in physics as well. And you actually use all those Monte Carlo events to calculate systematic errors, because the Monte Carlo events tell you how your apparatus responds to an understood sample of data, which has very clear distributions. And you can see what fraction of the event you detect. So when you observe a certain number of Higgs to photon after a certain number of steps, you apply exactly the same steps to the Monte Carlo data, and that tells you how many of the Higgs to photons you would have actually detected. Now, there is some uncertainty because the Monte Carlo is not correct, because we don't actually understand the physics in these regimes. We only have approximate models. However, the models are probably realistic enough to be able to give really pretty solid answers as to what the errors and the systematic errors are. So I think I will stop there. There is some more study which I might do next week. So I'd like to ask if there are any questions. The rest of these slides, and which is what the recorded ones, they look at a little more detail on how you, what happens when you have these square root of n type scenarios, and how you can analyze data under those circumstances. And there is a Colab. The Colabs are A, B, C, D. A and C are the two largest. No, B and C are the two largest. No, A and C are the two largest. And the C is the one that looks at normal distributions. The first big one studies exactly the Atlas experiment and tries to show you how, if you used Monte Carlo or a simulation, I mean a random generation of events, what the Atlas experiment looked like with different random numbers. All right, so I'm going to stop there. We have 10 minutes to go. All right, so I don't see any more chats. Are there any more questions? Did the fellow who wanted to, how did they visualize? Well, they have all those measurements. They have more measurements than they know what to do with. And so they just plotted they cleaned up the measurements and just plotted it. And these are all 3D pictures because these are 3D experiments. And they just use the 3D plotting program, and they just insert, like, let's do, let's look at this one here. So you can see here, so this visualization has two components. This red thing and these orange blobs, those must be experimental measurements, experimental observations. The orange lines correspond to taking the reconstructed, you've run this experimental, either a Monte Carlo event or a real event, it's not clear which one this is, could be either. They produce similar visualizations. You have run the, I mean, when you do, say, a Monte Carlo event, you actually take the event, the physics particles, you run the physics particles through the apparatus, you use random Monte Carlo generation to simulate the response of all your detectors, and then you run it through this analysis program, which takes these measurements and joins them, produce particles. So these orange things are not the raw measurements. They're the particles coming from the raw measurements of the particles, of what happens when you reconstruct these particle tracks. I should point out, reconstructing these, I used to write these codes, reconstructing these, these events which have hundreds of particles in them is not so trivial, because you have some uncertainty about how you join the tracks together. And so depending on the quality of the apparatus, that may or may not be so easy to do, because you have to use continuity about, because like, let's say this particle here would, any one of these particles would pass through chambers and produce ionization, but the same chamber would have other ionization from other particles. And you have to use some continuity principle to decide how you join the ionization in one chamber to an ionization in another chamber. Anyway, you then throw all that experimental data away and you just visualize these particles. And as you know the strength of the magnetic field, you can bend them in the magnetic field. All right, so that's the visualization. I think the visualization is not too difficult. It's useful and non-trivial, but it's not particularly challenging. All right, so well, the colors are just, they invented the colors. They used the orange in that case for charged particles and red for the photons, which is All right, so Ethan says, which homework? I asked you which homework you were asking about. Homework 2? Is Vibartha online? What question do you have about homework 2? We did have some questions about, which were, I think were answered on Piazza, about what the scope of homework 2 is. Did you look at that discussion on Piazza? All right, so why don't we, I think you will find Piazza has the answer to your question. If it doesn't, just send email. Because Vibartha, who answered it on Piazza, doesn't seem to be here. Anyway, what we've learned today is a particular example, the Higgs boson, but we've also learned how to do the analysis of a certain type of event, certain type of data acquisition, which say stems from political polling through physics experiments. It is not, it's very different from, say, the types of work you have to do to build self-driving cars and surveillance, face recognition and things. But so it has that's always going to be true. You're going to have these big data problems fall into different classes. And each class of problem has its own challenges. This physics experiment is actually, in terms of technology, it's relatively simple. And as far as I know, although it does use a little bit of deep learning for some side problems in the field, most of the analysis has not changed in style from when I did it, and in fact before when I did it. It's unchanged for 50 years or so. Because it's the analysis in terms of, it's effectively using histograms or variants of histogram scatter plots to identify signals. And it's also very it requires the physicist, it's not actually getting deep learning to tell you where to look. The physicist, as far as I know, typically has the intuition as to where to look, and this space is giant. With hundreds of particles, there are many things you could look at. The physicist chooses where to look. And in fact, if you're a PhD student in this area, you will spend a lot of your time building these giant apparatus and manning or womaning the apparatus as it takes data to make certain the data is correct. And there's no errors, because these are complicated apparatus, and you need to monitor them continuously to make certain they don't have faults. And so most of your time is actually spent on that, probably, of your 5 to 7 year PhD exposure. But then your actual thesis is written by the students taking a data sample, applying their intuition and physics knowledge to analyze a particular data sample to investigate a certain physics issue, like the probability the Higgs decays into a certain final state or something. All right, I will set the homework in the next day or so. And if you have any questions, just ask it on Piazza. I'd say, and I'm pretty certain homework 2 was answered on Piazza. Okay, I'll see you next week. Thank you.
Thank you.
Thank you.